What if some black holes weigh no more than a whisper, while others anchor entire galaxies in their grip? What if the smallest ones existed before the first stars were born, and the strangest ones live only in equations, waiting to be discovered? Tonight we journey through every fascinating type of black hole explained, from the stellar remnants left behind by dying suns to the quantum mysteries that blur the line between physics and imagination. Some black holes are silent wanderers, drifting invisibly through the Milky Way. Others blaze like cosmic beacons, feeding on stars and lighting up the darkness. And then there are the ones we have never seen, objects so bizarre they challenge everything we think we know about reality. These are not just cosmic curiosities. They are gateways to understanding the universe itself. They show us how matter collapses under its own weight, how galaxies form and evolve, and how space and time bend under gravity's absolute rule. From city-sized objects holding the mass of dozens of suns to monsters billions of times heavier, each type of black hole tells a different story. Some reveal the final moments of massive stars. Others may hold the secret to dark matter or the very birth of the universe. So settle in, let the stars drift past, and prepare to climb through all 5 levels of black holes. From the smallest stellar corpses to the most mind-bending possibilities in existence, this is the full scale of the universe's strangest and most powerful objects. Some black holes weigh no more than a single star, quiet remnants drifting through the cosmic void. Others are so immense, so monumentally vast, that they anchor entire galaxies in place, holding billions of stars in their gravitational embrace. And then there are the most mysterious kinds, the ones that haunt the edges of our understanding. Objects that may exist only in the realm of theory, hidden in equations and mathematical dreams, yet defying everything we think we know about the nature of reality itself. These objects exist on a spectrum that spans the unimaginable. At one end, we find black holes no heavier than our own sun, compact remnants of stellar death. At the other extreme lie giants that weigh as much as entire star clusters, cosmic behemoths that dwarf anything our everyday experience can comprehend. Between these extremes stretches a hierarchy of possibilities, each level revealing new mysteries about the nature of gravity, space, and time. The universe, in its infinite creativity, has found countless ways to create these gravitational wells. Some are born in the fiery collapse of massive stars, their formation marked by brilliant explosions that briefly outshine galaxies. Others may have emerged from the primordial chaos of the early universe, condensing from quantum fluctuations when the cosmos was barely a fraction of a second old. Still others grow slowly over billions of years, accumulating mass grain by grain until they become the gravitational masters of entire galaxies. Each of these formation pathways leaves distinctive signatures, clues we can read if we know where to look. A black hole born from a massive star will often have a companion star nearby, evidence of its origin in a binary system. A primordial black hole, if we could identify one, would have no such companion, no parent star to trace its lineage back to. A supermassive black hole will sit at the center of a galaxy, surrounded by billions of stars whose motions reveal its presence. Today, we will climb together through all 5 levels of black holes, ascending step by step through this cosmic hierarchy. From the smallest stellar corpses, born in the violent death throes of massive stars, to the most mind-bending possibilities in the universe, concepts that stretch the very fabric of what we consider possible. But before we begin that journey, before we venture into the darkness, let us pause for a moment and ask ourselves a fundamental question. What exactly is a black hole? The question seems simple on its surface. But the answer takes us to the very edge of physics, to places where our intuitions fail and mathematics becomes our only guide. To understand black holes, we must first understand how profoundly gravity can warp the universe around us, bending not just the paths of objects through space, but the very nature of space and time themselves. At its simplest, at its most elegant core, a black hole is a region of space where gravity has become so overwhelming, so utterly dominant, that nothing, not even light itself, can escape its pull. Imagine for a moment the possibility of compressing the entire mass of our Sun, that brilliant sphere of plasma that warms our days and lights our skies, into a sphere just a few kilometers wide. Picture all that stellar matter, all that energy and mass, crushed down into something no larger than a small city. This is not merely compression in the ordinary sense, not like squeezing water from a sponge. This is compression taken to its absolute limit, where the very atoms that make up matter are crushed beyond recognition, where electrons and protons are forced together, where even the fundamental particles themselves cease to exist in their familiar forms. What remains is something far stranger, a concentration of mass so extreme that it creates a tear in the fabric of reality itself. The resulting gravitational pull would be so extraordinarily strong that it bends the very fabric of space and time around it, warping reality itself. It creates what we might think of as a cosmic trapdoor, a one-way passage with absolutely no possibility of return. This boundary, this point of no escape, is known as the event horizon. It is the threshold beyond which escape becomes physically impossible, where the normal rules of cause and effect begin to break down in ways that challenge our deepest intuitions about how the universe works. Think of the event horizon not as a physical surface, but as a mathematical boundary in space-time. There is nothing solid there, no wall or barrier you could touch. It is simply the point where the escape velocity equals the speed of light. Inside that boundary, even travelling at light speed directly away from the centre would not be enough to escape. You would be pulled inexorably inward, no matter how fast you tried to flee. Near the event horizon, time itself begins to behave strangely. If you could somehow watch a clock falling toward a black hole from a safe distance, you would see it tick slower and slower as it approached the boundary. At the event horizon itself, from your perspective, time would appear to stop completely. The clock would seem frozen, eternally suspended at that threshold, though from the perspective of the clock itself, it would pass through normally and continue falling inward. This strange warping of time creates one of the most profound paradoxes in black hole physics. An observer, watching from afar, would never actually see anything cross the event horizon. Objects would appear to slow down asymptotically, their light becoming increasingly redshifted and dimmed, frozen forever at the boundary. Yet from the perspective of the infalling object, nothing special happens at the event horizon. It crosses through smoothly and continues falling toward the singularity at the center. Anything that crosses this invisible boundary, whether it is matter, energy, or even information itself, becomes part of the black hole forever. It is drawn inexorably inward, compressed and stretched in ways that defy imagination. And yet, for all their terrifying reputation in popular culture, for all the dramatic imagery of cosmic destroyers, black holes are not actually cosmic vacuum cleaners roaming through space, actively hunting down stars and planets to devour. This is a common misconception worth dispelling. If our Sun were suddenly replaced by a black hole of equal mass, the Earth would not be sucked in. Our planet would continue orbiting exactly as it does now, following the same gravitational pull, just in permanent darkness. Black holes only become dangerous when you venture close to them, when you cross into the region where their gravity becomes overwhelmingly strong. They are instead the natural outcome of physics pushed to its absolute extremes, the inevitable result when the universe follows its own laws to their logical conclusion. When massive stars collapse catastrophically under their own immense gravity, when matter piles up past certain critical thresholds that nature has established, or when the universe bends to quantum rules we still struggle desperately to understand, black holes emerge as the inevitable conclusion, as natural as water flowing downhill. In many ways, black holes represent the universe at its most honest, most raw. They are what happens when gravity wins completely, when no other force can resist its pull. They are the endpoints of certain cosmic processes, the final states where matter can go but never return from. In this sense, they are not cosmic aberrations or violations of natural law, but rather the most perfect expressions of gravity's fundamental nature. But here is where the real mystery deepens, where the story becomes truly fascinating. Not all black holes are created equal. Not all follow the same path or share the same characteristics. Some form directly from dying stars, stellar remnants only a few times heavier than our own sun, compact and relatively modest by cosmic standards. Others grow into absolute monsters, behemoths, millions or even billions of times more massive than our star, dwelling at the hearts of galaxies like ancient cosmic engines. Consider the range of possibilities this represents. The smallest black holes we know of might weigh just 3 times the mass of our sun. The largest could weigh 40 billion times that much. That is a difference in scale of over 10 billion, a range that spans from a compact object the size of a city to a region of space larger than our entire solar system. Within this enormous spectrum lie countless variations, each with its own story, its own origin, its own role in the cosmic drama. And then, beyond these categories we can observe and measure, there are black holes predicted purely by equations, objects conjured from mathematics, but never yet glimpsed by our telescopes or instruments. These theoretical entities challenge the very boundary between rigorous science and pure speculation, dancing on the edge between what is and what might be. Some of these theoretical black holes might be smaller than atoms, existing at scales where quantum mechanics and gravity collide in ways we do not yet understand. Others might exist in dimensions beyond the 3 of space and 1 of time that we experience. Still others might be connected by bridges through space-time, creating shortcuts across the universe that seem to belong more to science fiction than science fact. That is precisely where our journey begins tonight. Over the chapters that follow, we will climb together, step by careful step, through the complete hierarchy of black holes. From stellar corpses cooling in the darkness to quantum enigmas smaller than atoms, this is the full scale of the universe's strangest and most powerful objects. A complete tour through nature's most extreme possibilities. Each level will reveal something new, something unexpected about how the universe works when pushed to its limits. We will see how black holes shape the evolution of galaxies, how they might hold clues to the nature of dark matter, how they test our most fundamental theories of physics, and how they challenge us to imagine realities stranger than anything our ancestors could have dreamed. So settle in. Let your mind drift among the stars and prepare yourself as the journey into the cosmic darkness begins. The story of black holes, like so many cosmic tales, begins with stars. Those brilliant furnaces of fusion that light up galaxies across the observable universe, beacons of energy burning for billions of years. But, like absolutely all things in this universe, bound by time and entropy, stars have finite lifespans. They are not eternal, though they may seem so from our brief human perspective. Stars are remarkable engines, converting mass into energy through the process of nuclear fusion. In their cores, hydrogen atoms are forced together under immense pressure and temperature, fusing into helium and releasing tremendous amounts of energy in the process. This energy creates an outward pressure that balances the inward pull of gravity, maintaining a delicate equilibrium that can last for billions of years. For most of a star's life, this balance holds steady. The star shines peacefully, burning its fuel at a rate determined by its mass. Smaller stars like red dwarfs burn slowly and efficiently, potentially shining for trillions of years. Stars like our Sun burn at a moderate rate, with lifespans of about 10 billion years. But massive stars, those giants many times heavier than our Sun, burn fierce and fast, exhausting their fuel in just a few million years. When the most massive among them finally reach their end, when their fuel is exhausted and their cores can no longer sustain the fierce nuclear reactions that have kept them shining, they do not fade quietly into the night. They do not go gentle into that good night. Instead, they collapse in upon themselves with incredible violence, triggering explosions so unimaginably powerful that they outshine entire galaxies for a brief, brilliant moment. What remains after this chaos settles, after the shock waves spread and the light fades, can be something truly extraordinary. A stellar black hole. The transition from star to black hole happens in stages, each one more dramatic than the last. As a massive star ages, it burns through its hydrogen, then begins fusing heavier elements. Helium fuses into carbon and oxygen. These fuse into neon, magnesium, silicon. Each stage happens faster than the last, each one releasing less energy. Finally, the star begins creating iron in its core. Iron is special, uniquely important to this process. Iron cannot be fused to release energy. It is the end point of fusion, the element where the process stops being energy positive and becomes energy negative. When iron accumulates in the core, the star's fate is sealed. Without fusion to provide outward pressure, there is nothing left to hold the core up against gravity's relentless inward pull. Not every star in the cosmos qualifies for this dramatic fate, this violent transformation. Our own Sun, that familiar yellow dwarf that has warmed Earth for billions of years, is far too small, too lightweight to meet the requirements. It will die more gently, more peacefully, eventually swelling into a red giant before casting off its outer layers and becoming a white dwarf, a dense ember slowly cooling over trillions of years. White dwarfs represent one possible end point for stellar evolution, but not the one that leads to black holes. A white dwarf is held up by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too close together. This pressure can support objects up to about 1.4 times the mass of our Sun, a limit known as the Chandrasekhar limit. Beyond that mass, even electron degeneracy pressure is insufficient. For stars that exceed this limit but are not quite massive enough to form black holes, there is another possible fate: neutron stars. These are objects where the collapse has overcome electron degeneracy, pressure, crushing electrons and protons together to form neutrons. Neutron stars are extraordinarily dense, packing more than the mass of our Sun into a sphere just 20 kilometers across. But they are still not black holes. They are held up by neutron degeneracy pressure, another quantum effect. To create a stellar black hole, you need something far more massive. You need a true giant among stars, usually one at least 20 times heavier than our Sun, a stellar behemoth burning fierce and hot and fast. Once such a star finally exhausts its nuclear fuel, burning through element after element in its core, until even iron accumulates and fusion can proceed no further. Its core caves in on itself in a fraction of a second. The collapse happens almost unimaginably fast. In less time than it takes to blink, the core of the star, an iron ball about the size of Earth, collapses to a point just a few kilometers across. The outer layers of the star, no longer supported, fall inward at speeds approaching a quarter of the speed of light. When they hit the incompressible core, they bounce back outward in a shockwave that tears the star apart. This is a supernova, one of the most energetic events in the universe. For a few weeks, a single dying star can outshine all the other stars in its galaxy combined. The explosion hurls most of the star's mass out into space, enriching the interstellar medium with heavy elements forged in the star's core and in the supernova itself. These elements, scattered across light years, will eventually become part of new stars, new planets, perhaps new life. In that catastrophic instant, gravity overwhelms every other force in nature. It crushes matter to densities that are genuinely unimaginable by everyday standards, packing more mass into a smaller space than seems possible. The result is an object that weighs somewhere between 3 and 100 times the mass of our Sun, yet somehow fits into a sphere no larger than a single earthly city, no wider than the distance you might drive in an afternoon. At the center of this collapsed core, if the star was massive enough, lies a black hole. The exact mass limit that determines whether a stellar remnant becomes a neutron star or a black hole is still somewhat uncertain, but it is thought to be somewhere between 2 and 3 solar masses. Above that limit, no known force can prevent complete gravitational collapse to a singularity. Pause for a moment and truly try to picture that extraordinary scale, that impossible density. A black hole, just a few kilometers wide, compact enough to fit within the boundaries of a metropolitan area, yet containing the mass of dozens of entire suns. If we could somehow replace the core of Earth with such an object, if we could swap our planet's heart for a stellar black hole, our entire world and absolutely everything on it would be swallowed almost instantly, compressed down beyond recognition. The Earth would not simply fall into the black hole. It would be torn apart by tidal forces long before reaching the event horizon. The difference in gravitational pull between the near side and far side of our planet would be so extreme that rock itself would flow like water, stretching and compressing until the entire globe was reduced to a stream of matter spiraling into the darkness. This process of being stretched and torn apart by tidal forces has a wonderfully evocative name in physics: spaghettification. As an object approaches a black hole, the gravitational pull on the side nearest the black hole becomes much stronger than the pull on the far side. This difference in gravitational force, called a tidal force, stretches the object along the direction pointing toward the black hole while compressing it in the perpendicular directions. The object is literally stretched like a strand of spaghetti, pulled longer and thinner until it is torn apart at the molecular and then atomic level. For a human falling into a stellar black hole, spaghettification would begin long before reaching the event horizon. Your feet, being closer to the black hole than your head, would experience much stronger gravity. You would be stretched vertically while being compressed horizontally, a profoundly unpleasant experience. Eventually, the tidal forces would exceed the strength of chemical bonds, and you would be pulled apart into a stream of atoms, all falling inexorably toward the event horizon. Interestingly, for supermassive black holes, the tidal forces at the event horizon are actually quite weak. The event horizon is so far from the center that the difference in gravitational pull across a human-sized object would be negligible. You could, in theory, cross the event horizon of a supermassive black hole without immediately being torn apart. Of course, you would still be doomed, still falling toward the singularity at the center, where tidal forces would eventually become infinite. The scale is so extreme, so far removed from everyday experience, that ordinary comparisons barely begin to capture it. Imagine trying to compress the entire Himalayan mountain range, all those towering peaks and vast masses of rock, into something the size of a small pebble you could hold between your fingers. Or picture taking the entire human population of the world, all 8 billion people, and somehow compressing them into a single grain of sand. That is the kind of density we are contemplating here. That is the realm we have entered. To put it in more technical terms, the density at the center of a black hole, at what we call the singularity, is thought to be infinite. All the mass is compressed into a point of zero volume, creating infinite density. Of course, this is where our current physics breaks down completely. We do not really know what happens at the singularity. Our equations produce infinities, which usually signals that we are missing something fundamental, that a deeper theory is needed to describe what truly occurs at those extreme conditions. The singularity represents perhaps the deepest mystery in all of physics. Is it truly a point of infinite density, or does quantum mechanics somehow prevent the collapse from reaching such an extreme state? Does space-time itself become granular or discrete at such small scales, preventing the formation of a true mathematical point? These questions remain unanswered, awaiting a theory that can successfully merge quantum mechanics with general relativity. But here is a puzzle that naturally arises. How do we find something that, by its very definition and nature, gives off absolutely no light whatsoever? How do we detect an object that is fundamentally invisible, that by definition cannot be seen directly? This challenge has occupied astronomers for decades. You cannot simply point a telescope at a black hole and see it the way you would see a star or planet. The black hole itself is dark, a void against the background of space. Even if it is there, even if it is massive and nearby, it remains hidden from direct view. Finding black holes requires cleverness, patience, and a deep understanding of how gravity shapes the universe around these invisible objects. The answer, elegant and clever, lies not in the black hole itself, but in its surroundings, in the effects it has on everything nearby. A black hole may be completely invisible on its own, a void in space that emits nothing, but its presence is revealed clearly by the gravitational havoc it causes in its immediate neighborhood. When a stellar black hole is paired with a companion star, locked in a binary dance across the millennia, it can gradually steal gas from its larger, more visible partner. That stolen gas does not fall straight into the black hole in a simple plunge. Instead, it swirls around first, spiraling inward while forming a spinning disk of superheated material, a structure astronomers call an accretion disk. Binary star systems are common in the universe. More than half of all stars exist in multiple star systems, orbiting around common centers of mass. When one member of such a binary becomes a black hole, the system takes on fascinating new dynamics. The black hole, though invisible, exerts a gravitational pull on its companion, causing it to orbit in ways that reveal the black hole's presence. This disk does not fall quietly. As the gas orbits closer and closer to the event horizon, friction and gravitational forces heat it up to temperatures of millions of degrees. At such extreme temperatures, the disk begins to glow brilliantly in X-rays, producing signals powerful enough and distinctive enough to travel across thousands of light years and reach our telescopes here on Earth. The physics of accretion disks is complex and beautiful. The gas does not simply fall straight in because it has angular momentum. a property that makes it want to continue orbiting. As it spirals inward, it rubs against other parts of the disk, converting orbital energy into heat through friction. The inner parts of the disk, moving faster and experiencing more friction, heat up to higher temperatures than the outer parts. Near the event horizon, where the disk is hottest, temperatures can reach 100 million degrees or more. At these temperatures, the gas emits primarily in X-rays, light far too energetic for our eyes to see, but detectable by specialized telescopes in space. This X-ray emission is the signature we look for when hunting for black holes in binary systems. By carefully scanning the skies with specialized X-ray telescopes orbiting above our atmosphere to avoid interference, astronomers can pick out these cosmic beacons shining in wavelengths invisible to human eyes. These X-ray sources become signposts, pointing toward the hidden presence of black holes lurking in the darkness. The first X-ray telescopes were launched in the 1960s and 70s, opening an entirely new window on the universe. Before then, we were limited to observing the cosmos in visible light and radio waves. X-ray astronomy revealed a violent, energetic universe hidden from our eyes, full of neutron stars, supernovae, and yes, black holes. We can also detect stellar black holes through gravity itself, through the invisible hand that shapes orbits across the cosmos. If a visible star appears to be orbiting around an unseen companion, dancing through space as if pulled by an invisible partner, and that companion's mass turns out to be far too great to be anything ordinary like a neutron star or white dwarf, then the explanation becomes clear and inescapable. A black hole must be present, hidden, but undeniable. Astronomers can measure the orbit of a visible star with great precision. By watching how it moves over months and years, they can determine the mass of whatever it is orbiting, even if they cannot see that companion directly. If the companion is too massive to be a neutron star, which have a maximum mass of about 2 to 3 times the Sun's mass, then it must be a black hole. This technique, called the radial velocity method, has been instrumental in confirming the existence of stellar black holes. By measuring tiny shifts in the spectrum of the visible star, caused by its motion toward and away from us as it orbits its invisible companion, astronomers can reconstruct the entire orbital system and determine the mass of the hidden object. And thanks to revolutionary new instruments like the Laser Interferometer Gravitational Wave Observatory, known as LIGO, and its European counterpart Virgo, we now have yet another extraordinary tool in our arsenal. These remarkable detectors are listening with almost unbelievable sensitivity for the faint ripples in space-time itself created when two black holes collide and merge in a cosmic embrace. LIGO represents a triumph of engineering and physics. It uses laser beams travelling through 4-kilometre-long tubes to measure changes in distance smaller than the width of a proton. When a gravitational wave passes through Earth, it slightly stretches and compresses space itself, changing the distance the laser beam travels by an almost inconceivably tiny amount. Yet LIGO can detect this change. These gravitational waves are like drum beats echoing through the fabric of the universe, tremors in reality itself that tell us precisely where these hidden objects are and what they are doing. Every detection is a triumph, a confirmation that we can now sense the universe in entirely new ways. The first direct detection of gravitational waves in 2015 was a historic moment, confirming a prediction Einstein made a century earlier and opening an entirely new field of astronomy. Since then, dozens of black hole mergers have been detected, each one providing new insights into how these objects form, evolve, and interact. Perhaps the most famous and historically significant example of a stellar black hole is an object called Cygnus X-1. Discovered in the 1960s during the early days of X-ray astronomy, located approximately 6,000 light-years away from us in the constellation Cygnus, it was one of the very first black holes ever confirmed with scientific certainty. At its heart lies a black hole roughly 21 times the mass of our Sun, locked in a close orbital dance with a massive blue supergiant star. The system's X-ray emissions were so extraordinarily strong, so impossible to explain by any other means, that they could not be ignored or explained away by conventional objects. The supergiant star in this system is slowly being consumed by its dark companion. Gas streams from the star toward the black hole, forming an accretion disk that glows brilliantly in X-rays. This emission, first detected by early X-ray satellites, was unlike anything astronomers had seen before. It was too bright, too energetic, too concentrated to come from an ordinary star. Over decades of careful study, using ever more sophisticated instruments and techniques, scientists proved beyond any reasonable doubt that Cygnus X-1 was indeed harboring a genuine black hole. The discovery was so significant, so foundational to our understanding, that it even sparked a playful bet between scientists. The brilliant physicist Stephen Hawking once wagered publicly that Cygnus X-1 would ultimately turn out not to be a black hole at all, that some other explanation would eventually emerge. But when the evidence piled up year after year, becoming overwhelming and undeniable, he gracefully conceded the bet, admitting with characteristic humour that gravity had once again proven itself to be the strongest and most inexorable force governing our universe. Hawking made his bet in part because, ironically, his own theoretical work had suggested that black holes might not be quite as black as originally thought. His discovery of Hawking radiation suggested that black holes could slowly evaporate over time. But the evidence for Cygnus X-1 being a black hole became impossible to deny, and Hawking acknowledged the reality with good humour. Based on what we now know, astronomers estimate that there could be millions upon millions of stellar black holes scattered across our Milky Way galaxy alone. Most of them lie completely dormant, not actively feeding on nearby stars or gas clouds, and so they remain invisible to us, undetectable by current methods. This is an important point to grasp. Most black holes are not actively consuming matter. They are not surrounded by bright accretion disks or emitting X-rays. They simply drift through space, invisible and silent, their presence betrayed only by their gravitational influence if anything happens to pass nearby. These dormant black holes are extraordinarily difficult to find. They drift silently through the galaxy like cosmic ghosts, wandering through the spaces between stars, completely undetectable unless we happen to stumble upon the subtle clues they leave behind in their gravitational wake. Some may wander alone forever, solitary travellers on journeys lasting billions of years, while others will eventually grow by consuming passing stars or by merging with fellow black holes in violent collisions that shake the very foundations of space. Imagine the Milky Way as a vast city and black holes as dark buildings with no lights on. Most of them blend into the darkness, invisible against the night sky. Only when something happens, when a car passes by casting headlights, or when lightning strikes nearby, do we catch a glimpse of these hidden structures. Similarly, we only see black holes when they interact with something that produces light or other detectable signals. Occasionally, a star wanders too close to a dormant black hole, and when it does, the results are spectacular. The black hole's tidal forces tear the star apart in what astronomers call a tidal disruption event. The star is stretched and shredded, its gas streaming toward the black hole and forming a temporary accretion disk. For a few weeks or months, the previously invisible black hole blazes with light as it consumes the star's remains, then fades back into darkness once the feast is over. These tidal disruption events are rare but incredibly valuable for studying black holes. They allow us to detect black holes that would otherwise remain hidden, and they provide insights into how matter behaves under extreme tidal forces. Each event is unique depending on the mass of the star, the mass of the black hole, and the geometry of the encounter. Stellar black holes are far more than just the remnants of dead stars, mere cosmic leftovers. They are nature's first clear demonstration of what happens when ordinary matter is pushed beyond all known limits, when density and gravity reach extremes that dwarf anything we can create or fully comprehend. They show us gravity's raw power, unchecked and absolute, operating at its most fundamental level. In the simplest terms, these black holes are genuine cosmic paradoxes. They are city-sized objects somehow holding the equivalent weight of multiple suns, invisible traps that we can only find and study through their shadows and the disturbances they create. They represent where the hierarchy of black holes truly begins, the foundation layer of this cosmic pyramid, and they are the first real step into a universe far stranger and more extreme than anything we experience here on Earth. Each stellar black hole is a laboratory where we can test our understanding of physics under extreme conditions. Near their event horizons, space and time are warped so severely that our ordinary intuitions completely fail. Time slows down, space curves back on itself, and the laws of physics as we know them approach their breaking points. By studying these objects, we learn about the universe at its most fundamental level. If stellar black holes are the small seeds of the black hole family, the foundation stones, and supermassive ones are the giants ruling at the centers of galaxies like cosmic monarchs, then what lies in the space between these extremes? Logic and reason suggest there absolutely must be middleweights, transitional objects heavier than stellar black holes, but not nearly as monumentally monstrous as the supermassive kind. This gap in the black hole family tree is not just a minor detail. It represents a fundamental question about how black holes grow and evolve over cosmic time. If we only had stellar black holes and supermassive black holes, with nothing in between, it would be like finding only mice and elephants in the animal kingdom, with no medium-sized creatures to connect them. The absence would demand explanation. These hypothetical objects are what astronomers call intermediate mass black holes. And despite how obvious their existence might seem, they represent one of the most genuinely puzzling mysteries in all of modern astrophysics, a missing piece in our cosmic puzzle. The search for intermediate mass black holes has been ongoing for decades, driven by both theoretical predictions and observational hints. They should exist if our understanding of black hole formation and growth is correct, yet they remain maddeningly elusive, hiding in places where observations are difficult or disguising themselves as other objects. On paper, in theory, they seem almost obvious, nearly inevitable. A stellar black hole can weigh anywhere from a few dozen solar masses up to perhaps 100 times the mass of our Sun, while a supermassive black hole can weigh millions or even billions of solar masses. Surely somewhere in between those vastly different scales, spanning orders of magnitude, there must exist black holes weighing hundreds or thousands of suns, filling in that apparent gap. The mathematics of black hole formation supports this idea. There is no physical law that prevents black holes from existing at these intermediate masses. The same processes that create stellar black holes could, under the right circumstances, create slightly larger ones. The same processes that grow supermassive black holes could be caught in progress. creating intermediate mass objects along the way. And yet, despite decades of searching, despite using our most powerful telescopes and most sensitive instruments, intermediate mass black holes remain some of the hardest and most elusive objects to definitively pin down. They hide from us, slipping through the cracks of our detection methods. Part of the difficulty is that intermediate mass black holes likely exist in environments that are hard to study. They might lurk in dense star clusters, in the outskirts of galaxies, regions crowded with stars where picking out individual objects is challenging. They might drift through intergalactic space, far from any bright matter that could reveal their presence. They might even hide at the centers of dwarf galaxies, too small to produce the dramatic signals we associate with supermassive black holes. What makes them so special and so important is not just their size alone, not merely where they fall on the cosmic scale. It is what they could potentially reveal about the evolution and growth of black holes across cosmic time. They may very well be the missing link in black hole evolution, the crucial intermediate step that explains how small stellar remnants, born from individual dying stars, could possibly grow into the behemoths millions of times more massive that we observe at the centers of galaxies. Consider the problem of supermassive black hole formation. We observe black holes weighing billions of solar masses at the centers of galaxies that formed less than 1 billion years after the Big Bang. But how did they get so big so fast? Starting from a stellar black hole of, say, 30 solar masses, and growing by consuming gas and stars, there simply has not been enough time for them to reach billions of solar masses through normal processes. Intermediate mass black holes might solve this puzzle. If the early universe somehow produced black holes weighing thousands or tens of thousands of solar masses, these could serve as seeds for supermassive black holes. Starting from a much larger initial mass, they could more easily grow to billions of solar masses in the time available, without intermediate black holes serving as stepping stones, as bridges between scales. It becomes genuinely difficult to understand how the universe managed to build its largest and most impressive structures in the time available since the Big Bang. So what do we actually know with certainty about these mysterious middleweights? Current estimates and theoretical models suggest that intermediate mass black holes should weigh anywhere from a few hundred solar masses on the lower end to perhaps 100,000 solar masses at the upper range. That is still relatively small when compared directly to the massive titans dwelling at galactic cores, but it is unimaginably huge, almost incomprehensibly massive, when compared to their stellar cousins born from individual stars. This range spans 2 orders of magnitude, from objects barely heavier than the most massive stellar black holes to objects approaching the smallest supermassive black holes. Somewhere in this range lies the transition from one type to another, though the boundary is not sharp or well defined. Imagine trying to compress the entire combined mass of a dense star cluster, hundreds or thousands of stars packed tightly together, into something physically no bigger than Earth's moon. That is the kind of territory we are contemplating, the realm we are trying to explore. The fundamental problem, the reason they remain so elusive, is that actually finding them is extraordinarily difficult. It is like chasing shadows through a darkened room, searching for something that barely interacts with its surroundings. Unlike supermassive black holes, which often dramatically light up their surroundings as brilliant quasars visible across billions of light years, intermediate mass black holes are typically faint, quiet, and often hidden in unremarkable locations. Supermassive black holes have a major advantage when it comes to detection. They sit at the centers of galaxies, surrounded by abundant gas and stars that they can consume. This feeding process creates bright, easily visible signals. Intermediate mass black holes, by contrast, likely exist in environments with less available fuel, making them dimmer and harder to spot. They do not usually feed on vast amounts of matter that would create obvious bright emissions. They do not always sit conveniently in places where we can easily spot them, like the exact centers of galaxies. Instead, they may lurk in globular clusters, ancient collections of stars orbiting in the halos of galaxies. Or they may wander through galactic outskirts, where observations are difficult and uncertain. Globular clusters are intriguing potential homes for intermediate mass black holes. These are dense, spherical collections of stars that orbit galaxies like satellites. Some globular clusters contain hundreds of thousands or even millions of stars packed into a relatively small volume. In the dense centers of these clusters, stars could collide and merge, potentially building up more massive objects over time, perhaps even intermediate mass black holes. Scientists hunting for these elusive objects have to rely on extremely subtle clues and indirect evidence. They look for unusual motions of stars that suggest an invisible massive object nearby, pulling on them gravitationally. They search for peculiar X-ray sources that are too bright to come from stellar black holes, but too faint to be supermassive ones, occupying that suspicious middle ground. One technique involves measuring the velocities of stars near the centers of globular clusters. If stars are moving faster than expected, based on the visible mass, something invisible must be pulling on them. By carefully measuring these velocities and mapping how they change with distance from the cluster center, astronomers can infer the presence of a central massive object. Another approach looks for ultraluminous X-ray sources, objects that emit more X-rays than typical stellar black holes, but less than supermassive ones. Some of these sources might be intermediate mass black holes actively feeding on nearby matter, though other explanations are also possible, making interpretation challenging. One of the most promising candidates discovered so far is an object located in a dense star cluster, detected through careful analysis of stellar motions and faint emissions. But even the best candidates remain somewhat uncertain, not quite confirmed beyond all doubt, leaving astronomers frustrated and intrigued in equal measure. The candidate in the globular cluster Messier 15 is particularly interesting. Observations suggest a dark object weighing several thousand solar masses at the cluster's center. But is it a single intermediate mass black hole, or a collection of smaller objects like stellar black holes and neutron stars? The evidence is tantalizing, but not yet definitive. Another candidate was found through gravitational wave observations. In 2019, LIGO and Virgo detected a merger that produced a black hole weighing about 140 solar masses, right at the lower end of the intermediate mass range. This was exciting, but raised new questions. Was this truly an intermediate mass black hole, or just an unusually large stellar black hole, and how did it form? The importance of finding intermediate mass black holes definitively extends far beyond simple cosmic inventory, beyond merely cataloguing what exists. If they truly exist in significant numbers, if we can prove they are real and common, they could fundamentally reshape our understanding of how galaxies themselves form and evolve over billions of years. Understanding the population of intermediate mass black holes would help us understand the entire black hole family tree. It would reveal how black holes of different masses are distributed across the universe, how common each type is, and how they interact with their environments. This knowledge, in turn, would illuminate the processes that govern galaxy formation and evolution. They might serve as the seeds, the starting points, that eventually grow into the supermassive black holes we observe today. They might explain how black holes millions of times the mass of our Sun could already exist less than 1 billion years after the Big Bang, when there should not have been enough time for slow, gradual growth through normal processes. Several formation scenarios have been proposed for intermediate mass black holes. They might form from the direct collapse of massive gas clouds in the early universe, bypassing the stellar phase entirely. They might result from runaway collisions in dense star clusters, where stars merge repeatedly to build ever more massive objects. They might grow from stellar black holes through unusually efficient accretion of gas. Each scenario makes different predictions about where we should find them and how common they should be. For now, despite our best efforts and increasingly sophisticated tools, intermediate mass black holes remain one of astronomy's most tantalizing unsolved mysteries. They are the missing middle children of the black hole family, predicted by logic and theory, but stubbornly refusing to reveal themselves clearly. Every new telescope we build, every new detection method we develop, brings us one step closer to finally catching one definitively and solving this cosmic mystery. The next generation of telescopes and detectors promises to shed new light on this mystery. Advanced gravitational wave observatories will detect more mergers involving intermediate mass black holes. Next-generation X-ray telescopes will be sensitive enough to spot fainter emissions from distant clusters. Radio telescope arrays will map the motions of stars in cluster centers with unprecedented precision. One way or another, intermediate mass black holes will either reveal themselves or prove to be far rarer than we expect, and either answer will teach us something profound. Now we arrive at the true giants of the cosmos, the undisputed monarchs of the black hole hierarchy, supermassive black holes. These are not merely large objects. They are structures so monumentally vast, so incomprehensibly heavy, that they anchor and shape entire galaxies, influencing billions of stars across hundreds of thousands of light years. To call these objects large is an understatement bordering on the absurd. They are not just bigger than stellar black holes, they are millions or even billions of times more massive. The difference in scale is so vast that comparing a stellar black hole to a supermassive one is like comparing a grain of sand to a mountain or a drop of water to the entire ocean. At the heart of nearly every large galaxy we observe, including our own Milky Way, there sits one of these cosmic giants, a gravitational anchor around which everything else revolves. Our galaxy's own supermassive black hole, known by the somewhat modest name of Sagittarius A star, weighs approximately 4 million times the mass of our Sun, yet occupies a region of space only about 17 times wider than our star. Sagittarius A star sits at the very centre of our galaxy, 26,000 light-years away from Earth. For decades, astronomers tracked the orbits of stars near the galactic centre, watching them whip around an invisible object at speeds reaching a significant fraction of the speed of light. Some of these stars complete their orbits in just a few years, despite being light weeks away from the centre. The only explanation is a supermassive black hole. In 2020, the Event Horizon Telescope collaboration released the first image of Sagittarius A star, showing the same characteristic ring of glowing matter around a dark shadow that they had previously captured for the black hole in Messier 87. Seeing the supermassive black hole at the heart of our own galaxy was a profound moment, bringing home the reality that we live in a galaxy harbouring one of these cosmic giants. But as enormous as that sounds, as difficult as it is to truly comprehend, Sagittarius A star is actually relatively small by supermassive black hole standards. Some of the largest specimens we have discovered weigh tens of billions of solar masses, objects so massive that our Sun would be utterly insignificant by comparison, barely worth noticing. The largest known supermassive black hole weighs roughly 66 billion solar masses. It resides at the center of a galaxy called TON 618, billions of light years away. Its event horizon is so large that light would take nearly a full week to travel from one side to the other. The entire orbit of Neptune around our Sun could fit comfortably inside its event horizon, with room to spare. To put this in perspective, imagine if our entire solar system, everything from the Sun out past Neptune and beyond, was somehow contained within the event horizon of one of these giants. The scale becomes almost meaningless, stretching our ability to conceptualize size and mass to its breaking point. When we try to visualize objects this large, our minds struggle. We have no everyday reference points for something that could swallow solar systems whole. The human brain evolved to understand objects at human scales, from centimeters to kilometers. Supermassive black holes exist at scales millions of times larger, in a realm where only mathematics can guide us. These monsters did not appear suddenly or spring into existence fully formed. They grew over billions of years, feeding patiently and relentlessly on gas clouds, dust, unfortunate stars that wandered too close, and even other black holes that they encountered and consumed. Some grew through violent mergers when galaxies collided, combining their central black holes into even larger ones. Others fed more steadily, gradually accumulating mass over cosmic time. The growth process is complex and still not fully understood. A supermassive black hole can grow by accreting gas from its surroundings, adding mass bit by bit over millions of years. It can grow by consuming entire stars that venture too close, tidally disrupting them and swallowing their remains. It can grow by merging with other black holes, combining masses in catastrophic collisions that send gravitational waves rippling across the universe. Galaxy mergers play a particularly important role in this process. When two galaxies collide and merge, their central supermassive black holes eventually sink toward the center of the newly formed galaxy. Over millions of years, they spiral toward each other, eventually merging into a single, even more massive black hole. These mergers are among the most energetic events in the universe, releasing more energy and gravitational waves than all the stars in the observable universe emit as light. The real mystery, the question that still puzzles astrophysicists, is how they grew so large, so quickly in the early universe. Observations have revealed supermassive black holes already in place less than 1 billion years after the Big Bang, when the universe itself was still young and galaxies were just beginning to form properly. That should not have been enough time for them to reach such enormous sizes through normal growth processes, yet there they were, already billions of times the mass of our Sun. This is known as the high redshift quasar problem. Quasars are supermassive black holes, actively feeding and shining brilliantly. When we observe quasars at high redshift, we are seeing them as they appeared in the very early universe, thanks to the time it takes light to reach us across cosmic distances. Some of these ancient quasars harbor black holes weighing billions of solar masses, existing when the universe was less than 1 billion years old. The problem is timing. Even if you start with a stellar black hole weighing 100 solar masses and assume it feeds continuously at the maximum possible rate, known as the Eddington limit, it would take longer than 1 billion years to grow to 1 billion solar masses. Yet we see such objects already existing when the universe was younger than that. Something must be missing from our understanding. Several solutions have been proposed. Perhaps black holes in the early universe could feed faster than the Eddington limit under certain special conditions. Perhaps they started from much larger seeds, intermediate mass black holes or primordial black holes, giving them a head start. Perhaps multiple smaller black holes merged rapidly to build up mass quickly. Each explanation has its proponents and challenges, and the truth may involve a combination of mechanisms. When supermassive black holes actively feed, when they draw in large amounts of matter from their surroundings, they do not do so quietly or subtly. The infalling material forms enormous accretion disks, spiraling structures of superheated gas and dust that can span light years across. These disks glow with such incredible intensity, radiating across the entire electromagnetic spectrum, that they can outshine all the billions of stars in their host galaxy combined. The accretion disks around supermassive black holes are cosmic powerhouses. As gas spirals inward, gravitational potential energy is converted to heat and light through friction and compression. The efficiency of this conversion is remarkable, far exceeding nuclear fusion. A supermassive black hole can convert up to 40% of the infalling mass into radiated energy, making them the most efficient energy generators in the universe. We call these brilliant beacons quasars, among the brightest and most energetic objects in the entire universe. Some are so luminous that we can detect them from billions of light years away, seeing them as they appeared when the universe was still in its infancy. They serve as cosmic lighthouses, visible across vast stretches of space and time. The word quasar comes from quasi-stellar radio source, reflecting how these objects appeared when first discovered in the 1960s. They looked like stars through optical telescopes, point sources of light, but their spectra and radio emissions were completely unlike any star. It took years to understand that these were not stars at all, but the active cores of distant galaxies powered by supermassive black holes. Quasars are so bright that they can outshine their entire host galaxies by factors of hundreds or even thousands. The light from the accretion disk around the central black hole drowns out the combined light from billions of stars. Only by carefully blocking out the quasar's light can astronomers study the galaxy surrounding it. Not all supermassive black holes feed actively at any given moment. Many, including our own Sagittarius A star, are relatively quiet right now, dormant or feeding only very slowly on sparse material. But even in their quiet state, their gravitational influence remains profound and far-reaching. Sagittarius A star is relatively quiet because there is not much gas available for it to consume in the galactic center. The region has been largely cleared out by previous episodes of feeding and by the powerful winds from massive stars. Occasionally, a gas cloud or unfortunate star wanders too close, providing a brief snack. But most of the time, the black hole sits quiescent, slowly sipping on a thin trickle of material. This alternation between active and quiet states appears to be common for supermassive black holes. They feed voraciously when gas is available, shining as quasars, then quiet down when the fuel runs out. The duty cycle varies from galaxy to galaxy, depending on the availability of gas and the history of mergers and interactions. They shape the orbits of stars near galactic centers, control the distribution of gas clouds across entire galaxies, and may even regulate star formation itself through their periodic outbursts of energy. When they do feed more actively, they can generate powerful jets of material, narrow beams of particles, and radiation that shoot out from near the event horizon at speeds approaching the speed of light. These jets are among the most mysterious and impressive phenomena associated with supermassive black holes. They emerge perpendicular to the accretion disk, shooting out from the poles of the black hole at relativistic speeds. Some jets are barely detectable, while others stretch for millions of light years, far beyond the galaxy that hosts them. The mechanism that produces jets is still debated, but it likely involves the black hole's rotation and magnetic fields threading through the accretion disk. As the disk rotates and the magnetic fields twist, they can channel some of the infalling material into narrow beams that are accelerated to nearly the speed of light. The energy for this process comes from the rotational energy of the black hole itself, or from the gravitational potential energy of infalling matter. These jets can extend for thousands or even millions of light years, punching through the galaxy and out into intergalactic space, reshaping the environment on truly cosmic scales. They are among the most energetic phenomena in the universe, powered entirely by matter falling into the black hole and the immense rotational energy these giants possess. Jets from supermassive black holes can have profound effects on their host galaxies and beyond. They heat the gas in and around galaxies, preventing it from cooling and forming new stars. They can trigger star formation in regions where they compress gas clouds. They can even affect the evolution of galaxy clusters, the largest gravitationally bound structures in the universe, containing thousands of galaxies. In some cases, jets create enormous cavities in the hot gas that fills galaxy clusters. These cavities, visible in X-ray images, can be hundreds of thousands of light years across, testifying to the immense power of the jets that created them. The energy required to excavate such cavities is staggering, equivalent to the entire energy output of our Sun over trillions of years. The discovery and study of supermassive black holes represents one of the great triumphs of modern astronomy. For decades, they were purely theoretical, predicted by equations, but never directly seen. Now, we have not only detected them indirectly through their effects, but we have even managed to image one directly. The journey from theoretical speculation to observational confirmation took decades of patient work. In the 1970s and 80s, astronomers found mounting evidence for supermassive black holes through observations of quasars and active galactic nuclei. In the 1990s and 2000s, detailed studies of stellar orbits near galactic centers provided compelling evidence. Finally, in the 2010s, direct imaging became possible. In 2019, the Event Horizon Telescope collaboration, using a network of radio telescopes spread across the entire Earth working in concert, captured the first ever direct image of a supermassive black hole's event horizon. The target was the giant at the center of the galaxy Messier 87, a black hole weighing about 6.5 billion solar masses located 55 million light-years away. The Event Horizon Telescope is not a single instrument, but a network of radio telescopes scattered across the globe, from Hawaii to Chile to Antarctica. By combining their observations using a technique called very long baseline interferometry, they effectively created a telescope the size of the Earth itself, achieving resolution sharp enough to see the shadow of a black hole's event horizon from millions of light years away. The image showed exactly what theory predicted: a bright ring of emission surrounding a dark central shadow, the shadow of the event horizon itself. It was the first time humanity had truly seen one of these objects directly, confirming decades of theoretical work and opening an entirely new window into studying them. The bright ring in the image is light from the accretion disk and from gas near the black hole, bent around the black hole by its intense gravity. Some of this light comes from the far side of the black hole, bent around to reach us. The dark shadow in the center is larger than the event horizon itself, representing the region from which light cannot escape or is bent away from us. Seeing this image was profound for scientists and the public alike. It made real something that had existed only in equations and computer simulations. It confirmed that our understanding of gravity, based on Einstein's general relativity, remains accurate even in the most extreme environments we can observe. Supermassive black holes are more than just the largest type of black hole. They are fundamental components of galaxy formation and evolution, cosmic engines that have shaped the universe we see around us. Without them, galaxies would look very different, would have evolved along entirely different paths. They are the beating hearts of galaxies, the anchors that have held cosmic structure together across billions of years of cosmic time. The relationship between supermassive black holes and their host galaxies is intimate and complex. Observations show a tight correlation between the mass of a galaxy's central black hole and properties of the galaxy itself, such as the mass of its central bulge and the velocity dispersion of its stars. This suggests that black holes and galaxies co-evolve, influencing each other's growth over cosmic time. This co-evolution is still not fully understood. Do black holes regulate galaxy growth through their energetic feedback, heating gas and preventing star formation? Or do galaxies feed their central black holes, providing the fuel for growth? The truth likely involves both processes working together in a complex dance that has played out across billions of years. Now we descend to an entirely different kind of mystery, traveling backward in time to the universe's earliest moments: primordial black holes. Unlike every other type we have discussed so far, these would not have formed from collapsing stars or from matter accumulating at galactic centers. Instead, they would have emerged directly from the Big Bang itself, born in the first fractions of a second after the universe began. The very concept of primordial black holes represents a radical departure from conventional black hole formation. Every other type of black hole we have discussed formed from matter that already existed, that underwent some process of collapse or accumulation. Primordial black holes, if they exist, would have formed directly from the structure of space-time itself in the earliest moments of cosmic history. The concept is both elegant and strange. In the extremely early universe, in those first fleeting moments after creation, conditions were unimaginably extreme. Matter and energy were compressed to densities we cannot recreate or fully understand. Space itself was far more turbulent and chaotic than anything we observe today. In the first microseconds after the Big Bang, the universe was unimaginably hot and dense, filled with a soup of fundamental particles and radiation. Space was expanding rapidly, but not uniformly. Quantum fluctuations created regions slightly denser than average and regions slightly less dense. Most of these fluctuations were tiny and smoothed out over time, but some might have been strong enough to trigger gravitational collapse. In certain regions, purely by chance, density fluctuations in this primordial soup might have been strong enough to collapse directly under their own gravity, creating black holes without needing a star to die first. These primordial black holes could have formed at almost any size, from microscopic ones smaller than atoms to massive ones rivaling stars, depending entirely on the specific conditions in each collapsing region. The mass of a primordial black hole would depend on the size of the region that collapsed. A region containing the mass of a mountain, collapsing in the early universe, might create a black hole with that mass. A larger region might create a stellar mass black hole, or even larger. The spectrum of possible masses is wide, limited only by the properties of the density fluctuations in the early universe. The smallest primordial black holes, if they formed, might have masses as tiny as a few micrograms, smaller than a grain of sand. The largest might weigh thousands of solar masses, bridging the gap between stellar and intermediate mass black holes. Each mass range would have different implications for cosmology and astrophysics. The truly fascinating aspect of primordial black holes is that they could still be around today, scattered throughout the cosmos. Unlike stellar black holes, which we can trace back to specific dying stars, primordial ones would have no parent star, no supernova remnant, no obvious origin point. They would simply exist, ancient relics from the universe's birth, drifting silently through space. If primordial black holes exist, they would be among the oldest objects in the universe, formed when the cosmos was less than a second old. They would have witnessed the entire history of cosmic evolution, from the formation of the first atoms through the birth of the first stars and galaxies to the present day. They would be, in a very real sense, fossils from the moment of creation. Some scientists have proposed an intriguing and audacious possibility. What if primordial black holes account for some or even most of dark matter, that mysterious invisible substance that makes up roughly 85% of all matter in the universe? We know dark matter exists from its gravitational effects, but we have never directly detected the particles it might be made of, despite decades of searching. Dark matter is one of the great unsolved mysteries of modern physics. We can see its effects everywhere we look. Galaxies rotate faster than they should based on their visible matter, held together by the gravity of invisible dark matter. Galaxy clusters contain far more mass than we can see, revealed by gravitational lensing. The cosmic microwave background and large-scale structure of the universe require dark matter to explain their properties. Yet despite decades of searching with increasingly sensitive detectors, we have never detected a dark matter particle directly. Experiments deep underground, shielded from cosmic rays, watch for the faint signal of dark matter particles colliding with normal matter. Other experiments at particle accelerators try to create dark matter particles in high-energy collisions. So far, all have come up empty. What if the answer is not exotic particles at all, but instead countless primordial black holes scattered throughout the cosmos, too small and too spread out to detect individually? If true, that would mean the missing mass of the universe is literally made of invisible black holes drifting silently through space, an invisible population of ancient objects pervading everything. This idea is appealing because black holes are made of ordinary matter, or more precisely, they are regions of severely warped space-time that form from ordinary matter. We would not need to invoke new particles or physics to explain dark matter. The required black holes would simply be a consequence of conditions in the very early universe. Some theoretical models suggest that trillions upon trillions of tiny primordial black holes could be passing through our solar system at any given moment, potentially even passing right through Earth itself without leaving any detectable trace. Their gravity would be so precisely localized and their individual size so incredibly small that we would not even notice their passage through normal matter. A primordial black hole weighing as much as an asteroid but no larger than an atom would have intense gravity in its immediate vicinity, but negligible effects beyond a tiny radius. It could pass through a planet without significantly disturbing it, like a bullet passing through mist. The gravitational tug would be too brief and too localized to affect the planet's orbit or internal structure noticeably. Of course, as intriguing as these ideas are, the mystery runs even deeper when we consider the implications. If primordial black holes formed in abundance in the early universe, they might also elegantly explain one of the major puzzles in cosmology. How did supermassive black holes grow so quickly? Observations clearly show that enormous black holes, already weighing billions of solar masses, existed less than 1 billion years after the Big Bang. But stellar black holes, born from dying stars, should not have had nearly enough time to grow that large through normal feeding processes. The universe was simply too young. Starting from a stellar black hole weighing tens or hundreds of solar masses, even with optimal conditions and maximal feeding rates, it is difficult to explain billion solar mass black holes less than 1 billion years after the Big Bang. The numbers simply do not add up using conventional growth mechanisms. Primordial black holes, acting as seeds, as ready-made starting points already containing significant mass, could have given the growth process a massive head start, allowing supermassive black holes to reach their observed sizes much more quickly and naturally. If primordial black holes, weighing thousands or even millions of solar masses, formed in the early universe, they could serve as the seeds for supermassive black holes. These seeds, already massive from the moment of their creation, could grow to billions of solar masses in the available time through normal accretion and mergers. The timing problem disappears if you start with a much larger initial mass. So far, though, despite the elegance of these ideas, the actual evidence remains frustratingly thin and uncertain. We have not yet directly observed any primordial black holes with certainty. Scientists search for them using multiple clever methods. They look for their gravitational effects, such as tiny distortions in starlight when one passes directly in front of a distant star, an effect called microlensing. Microlensing occurs when a massive object passes between us and a distant star. The object's gravity bends the star's light, causing the star to briefly appear brighter. The duration and shape of this brightening can tell us about the mass of the intervening object. If that object has the properties expected for a primordial black hole, it would provide evidence for their existence. Several surveys have searched for microlensing events caused by primordial black holes, watching millions of stars over years to catch the brief brightening that would signal a black hole passing in front. Some potential candidates have been found, but interpreting these events is tricky. Other objects, like brown dwarfs or rogue planets, can also cause microlensing, making it difficult to definitively identify primordial black holes. They search for potential bursts of radiation that might occur if a small primordial black hole finally evaporates completely through the process of Hawking radiation, releasing its remaining mass energy in a final flash. Each new telescope we build, each new experiment we conduct, gives us another opportunity to catch one in the act, to finally prove they exist. The smallest primordial black holes, if they formed, would have evaporated long ago through Hawking radiation. Only those weighing more than about 10 to the power of 11 kilograms, roughly the mass of a mountain, would still exist today. Smaller ones would have evaporated over the age of the universe, releasing their energy as particles and radiation. Detecting this evaporation would be a clear signature of a primordial black hole. But for now, they remain ghosts of theory, mathematical possibilities that have not yet crossed the threshold into confirmed reality. Still, the mere possibility is genuinely thrilling for scientists and dreamers alike. If we could somehow prove their existence definitively, primordial black holes would not just solve the persistent riddle of dark matter's identity, they would also forge a profound connection between the smallest scales of quantum physics and the largest scales of cosmology. They would serve as genuine fossils from the very birth of the universe itself, carrying within them secrets from the first instant of creation, from a time when the cosmos was smaller than an atom. Primordial black holes would be a bridge between particle physics and cosmology, between the quantum and the cosmic. They would carry information about the state of the universe in its first moments, about the density fluctuations that seeded all later structure, about the fundamental laws of physics operating under conditions we can never recreate in laboratories. Whether they turn out to be real or not, whether nature actually created them, the concept itself fundamentally reshapes our imagination about what black holes can be. Black holes, it turns out, may not exclusively be the final stage of stellar evolution, the endpoints of dying stars. They may also potentially be the very first structures the universe ever managed to build, the earliest objects to condense from the primordial chaos. This reversal of perspective is profound. Instead of being endpoints, black holes might also be beginnings. Instead of being products of death and decay, they might also be products of birth and creation. The universe, in its first moments, might have immediately begun creating the very objects that would later shape its evolution across billions of years. And if that turns out to be true, if evidence eventually confirms their existence, then the entire story of black holes is not just about death and gravitational collapse. It becomes equally a story about origins and beginnings, about the raw creative power unleashed at the universe's birth, about how structure emerged from chaos in those first impossible moments. When most people think of black holes, when they picture these objects in their minds, they naturally imagine enormous entities, monsters containing the mass of stars, or even entire galaxies compressed into impossibly small spaces. But what if black holes could also exist at the tiniest scales imaginable, at sizes smaller than a single atom, smaller even than the smallest subatomic particles we know? The leap from supermassive black holes weighing billions of suns to quantum black holes smaller than atoms is staggering. It spans 60 orders of magnitude or more, a range so vast that our minds struggle to comprehend it. Yet physics suggests that both extremes might exist, that black holes might span this entire incredible range of sizes. This is the strange and highly theoretical idea of quantum black holes, objects that exist at the very edge of what our current physics can describe. Unlike the black holes formed from collapsing stars or found lurking at galactic centers, quantum black holes belong to an entirely different frontier of physics. They exist in the mysterious space where our two best scientific theories, Einstein's general relativity and quantum mechanics, overlap and begin to clash in fundamental ways. This clash is not a minor technical detail. It represents one of the deepest problems in all of theoretical physics. General relativity and quantum mechanics are both extraordinarily successful theories, each tested to remarkable precision in its own domain. Yet they are fundamentally incompatible, based on different principles and making contradictory predictions when both should apply. General relativity explains beautifully how gravity shapes and warps the universe on large cosmic scales, governing the motion of planets and galaxies. Quantum mechanics, meanwhile, governs the strange, probabilistic, unpredictable world of subatomic particles, where certainty gives way to clouds of probability. Normally, these two frameworks stay comfortably in their own separate lanes, each supreme in its own domain. At everyday scales, and even at most astronomical scales, we can use one theory or the other without problems. General relativity handles planets, stars, and galaxies. Quantum mechanics handles atoms, molecules, and fundamental particles. The two rarely need to be applied to the same problem, so their incompatibility usually does not matter. But if matter were somehow compressed down to unimaginably small scales, to distances smaller than anything we can directly probe, both sets of laws would apply simultaneously. And there, at that boundary, neither framework is fully adequate or complete. They contradict each other in subtle but profound ways. This is the Planck scale, where both quantum effects and gravitational effects become equally important. At larger scales, gravity dominates, and quantum effects can be ignored. At smaller scales than ordinary quantum objects, gravity can be ignored, but at the Planck scale, both matter simultaneously, and our current theories cannot handle this. This is where the concept of Planck scale black holes emerges from pure theory. The Planck length, approximately 10 to the negative 35th meters, is theoretically the smallest meaningful unit of space itself, the scale at which the very concept of distance begins to break down. According to our current understanding of physics, a black hole of that scale would be almost inconceivably tiny, far smaller than a proton, far smaller than anything we can observe or measure directly. To put this in perspective, a Planck length is to an atom what an atom is to the observable universe. It is a scale so small that it defies comprehension. At this scale, quantum fluctuations in space-time itself become important. Space and time cease to be smooth continua and become a foaming quantum froth where the normal rules break down completely. Yet despite this incomprehensible smallness, it would still carry immense density, packing a surprising amount of mass into that impossibly tiny space. In theory, such an object would represent the ultimate meeting point of gravity in quantum physics, the place where these two great theories must somehow be reconciled. A Planck mass black hole would weigh about 20 micrograms, roughly the mass of a grain of sand. This does not sound like much, but packed into a Planck length, it represents a density beyond anything else in physics. Every known force and principle would be strained to its breaking point in such an object. But there is a fundamental catch, a problem that makes these objects even more theoretical. Tiny black holes, unlike their larger cousins, do not last for long periods. Thanks to Stephen Hawking's famous and revolutionary insight, we now believe that all black holes slowly evaporate over time through a quantum process called Hawking radiation. Hawking radiation is a quantum effect that occurs near the event horizon. Virtual particle pairs, which constantly pop in and out of existence throughout space due to quantum fluctuations, can be separated by the black hole's gravity. One particle falls in, while the other escapes. The escaping particle carries away energy, causing the black hole to lose mass over time. For stellar black holes, or supermassive ones, that evaporation process takes longer than the current age of the entire universe, making it completely irrelevant on any practical timescale. But a black hole as small as a particle, as tiny as a Planck scale object, would evaporate almost instantaneously in the blink of an eye, releasing its stored energy in a brief flash before vanishing completely from existence. The evaporation time of a black hole is proportional to the cube of its mass. Massive black holes evaporate incredibly slowly, while tiny ones evaporate incredibly quickly. A Planck mass black hole would evaporate in about the Planck time 10 to the negative 43 seconds, the shortest meaningful unit of time. It would exist for barely an instant before disappearing in a burst of energy. Could these miniature black holes actually exist anywhere in reality? Some scientists have speculated that they might have formed in the violent, extreme conditions of the very early universe, in those first moments after the Big Bang when energy densities were at their absolute peak. Others wonder more speculatively if high-energy collisions, like those produced inside our most powerful particle accelerators, such as the Large Hadron Collider, could briefly and fleetingly create them. The possibility of creating black holes in particle accelerators caused some public concern when the Large Hadron Collider was being built. Some worried that a microscopic black hole might be created and swallow the Earth. But physicists explained that even if such black holes could be created, which is extremely unlikely given current understanding, They would evaporate instantly through Hawking radiation, long before they could consume even a single additional particle. Though so far, no evidence whatsoever has been found, despite careful searching, and most physicists consider it extremely unlikely. Even without any direct proof of their existence, even if they turn out to be purely mathematical constructs, the idea of quantum black holes is far from idle speculation or science fiction. The absence of evidence is not surprising. Quantum black holes, if they could be created, would exist for unimaginably short times and would be extraordinarily difficult to detect. They would evaporate before we could observe them directly, leaving only indirect signatures that would be hard to distinguish from other quantum processes. Quantum black holes serve as a crucial thought experiment, a theoretical tool that forces physicists to confront one of the deepest and most persistent mysteries in all of science. How can we unify quantum mechanics with general relativity? How can we create a single coherent framework that explains both the very large and the very small, both galaxies and particles? This quest for unification has occupied the best minds in physics for decades. String theory, loop quantum gravity, and other approaches all attempt to reconcile these two great theories, to find a deeper framework that contains both as special cases. Quantum black holes represent the testing ground for these theories, the place where they must make predictions that differ from both general relativity alone and quantum mechanics alone. If such objects could ever be shown to exist, even fleetingly for the briefest instant, they would provide an absolutely critical clue toward building what physicists call a theory of everything, a single unified framework that explains all of physics, from the quantum to the cosmic, from the smallest to the largest. A theory of everything would not just unify gravity with the other forces, it would explain why the universe has the properties it does, why certain constants have the values they have, perhaps even why there is something rather than nothing. Quantum black holes, sitting at the intersection of quantum mechanics and general relativity, would be key to testing and validating such a theory. Quantum black holes may never be directly observed by any instrument we can conceive of building. They may remain forever in the realm of pure theory and mathematics. But their significance lies not in whether they exist, but in what they represent conceptually. They are not about devouring stars or shaping galaxies like their larger cousins. They are about the edge of knowledge itself, about the frontier where our current theories begin to fail and break down, where new physics must inevitably emerge to fill the gaps. In their tiny theoretical horizons, in those impossibly small regions of warped space-time, could lie answers to some of the universe's greatest and most profound questions about the nature of reality itself. Questions like, is space-time continuous or discrete at the smallest scales? What is the true nature of the Big Bang singularity? Can information truly be destroyed, or is it preserved in subtle quantum correlations? What determines which mathematical possibilities nature actually implements? These questions, and many others, find their testing ground in the physics of quantum black holes. One particular question has haunted physicists for decades: the black hole information paradox. When matter falls into a black hole, what happens to the information it contains? According to quantum mechanics, information can never be truly destroyed. Yet according to general relativity, anything that crosses the event horizon is lost forever, seemingly violating this principle. Hawking radiation, the process by which black holes evaporate, appears to be completely random, carrying no information about what fell in. This paradox strikes at the heart of our understanding of reality. If information can be destroyed in black holes, then quantum mechanics is incomplete or wrong. If information cannot be destroyed, then either general relativity is wrong about what happens inside black holes, or information somehow escapes in ways we do not yet understand. Resolving this paradox may require a complete reworking of our theories at the most fundamental level. We have climbed together through the 5 main levels of black holes, ascending from stellar remnants born in supernova explosions to quantum mysteries smaller than atoms. But the story does not end there, does not conclude neatly with those 5 categories. Beyond these main types, scientists have proposed and discovered other fascinating kinds of black holes, some confirmed through observation, others remaining purely speculative. The universe, as we have seen again and again, is far more creative and varied than we might expect. Just when we think we have catalogued all the possibilities, new observations or new theories reveal additional varieties, additional wrinkles in the cosmic tapestry. Black holes, it turns out, come in more flavours than the main 5 categories we have explored. Think of these as the bonus round, the additional chapters where established reality and theoretical imagination meet and blend together in intriguing ways. One of the most exciting and scientifically significant discoveries in recent years has been the confirmation of binary black holes. These are pairs of black holes locked together in an orbital dance around one another, bound by mutual gravity, circling through space like cosmic partners. Binary systems are common throughout the universe. Most stars exist in binary or multiple star systems. When massive stars in binary systems die, they can leave behind pairs of black holes, still orbiting each other. These systems are laboratories for testing general relativity under extreme conditions. For billions of years, these paired objects circle closer and closer together, their orbits gradually decaying as they lose energy to gravitational wave radiation. The spiral continues, tightening, until finally they collide and merge in a cataclysmic release of pure energy, a cosmic collision of almost unimaginable violence. The inspiral process can take billions of years for widely separated black holes, but accelerates dramatically as they approach merger. In the final seconds before collision, they orbit each other thousands of times per second, moving at significant fractions of the speed of light, their event horizons nearly touching. When this catastrophic merger happens, when 2 black holes finally unite, ripples spread outward across the fabric of space-time itself, travelling at the speed of light in all directions. We call these ripples gravitational waves, literal vibrations in the structure of reality, and they were first detected directly in 2015 by the LIGO Observatory. The merger of 2 black holes is one of the most energetic events in the universe. In the final fraction of a second, they can radiate more power in gravitational waves than all the stars in the observable universe emit as light. This energy comes from the orbital energy of the system and from the mass of the black holes themselves, converted to gravitational radiation through Einstein's famous equation E = mc². That momentous detection confirmed not only Einstein's century-old predictions about gravitational radiation, but also proved definitively the existence of black hole pairs colliding in distant galaxies billions of light years away. Today, every new detection of merging black holes adds another chapter to the hidden history of these cosmic duets, revealing the population and behavior of black holes across the universe. Since that first detection, gravitational wave observatories have detected dozens of black hole mergers, each one providing new data about black hole populations, masses, spins, and formation mechanisms. Each detection is a glimpse into violent events occurring across cosmic distances, events that would be completely invisible to conventional telescopes. The data from these mergers has revealed surprises. Black holes more massive than expected, black holes with unexpected spins, mergers occurring in environments we did not predict. Each surprise teaches us something new about how black holes form and evolve, refining our understanding of these extreme objects. Then there is an even stranger idea, one that remains firmly theoretical: white holes. If black holes are cosmic objects that trap absolutely everything that comes near, regions from which nothing can escape, then white holes are their hypothetical opposites, mirror images in the equations. Objects that nothing can enter, from which matter and energy are only expelled outward. The equations of general relativity are symmetric in time. If you reverse the direction of time in the equations, you get solutions that are equally valid mathematically. Black holes are solutions where matter falls in and nothing comes out. Reversing time gives you white holes, solutions where matter comes out and nothing falls in. They have never been observed in nature, and most physicists genuinely doubt they exist anywhere in our universe. But the concept is deeply intriguing from a theoretical perspective. Some mathematical models even imagine that a white hole could theoretically be the other end of a black hole, the exit point, connected by a tunnel through space-time called a wormhole. The idea of black holes connected to white holes through wormholes is a staple of science fiction, but it has a basis in the mathematics of general relativity. The simplest black hole solution, the Schwarzschild solution, mathematically includes both a black hole region and a white hole region connected by a wormhole. However, this solution is probably not physically realistic. In realistic situations, the wormhole connection would be unstable, pinching off before anything could traverse it. Quantum effects would likely prevent the formation or persistence of such connections, and we have never seen any evidence for white holes, which should be just as conspicuous as quasars if they existed and were actively expelling matter. While this remains absolutely and firmly in the realm of speculation, more science fiction than science at this point, it captures the imagination beautifully as a playful what-if scenario in our cosmic story. It reminds us that the mathematics of general relativity contains possibilities that nature may or may not choose to actually implement. Mathematics can describe many things that do not exist in physical reality. The equations allow for solutions that are mathematically consistent but physically impossible. White holes may be one such solution, beautiful on paper but absent from the actual universe. Or they may exist in some form we have not yet imagined. Only continued observation and theoretical work will tell. These bonus examples, these additional categories beyond the main five, remind us that black holes are not just astrophysical objects to be catalogued and studied. They are also powerful thought experiments, theoretical tools for testing the limits of our theories and observations, for exploring what is possible within the laws of physics. Every time we discover a new type of black hole or confirm the existence of a predicted variety, we learn something profound about the universe. Every time we find that a predicted type does not exist, we learn something equally important about what constraints nature imposes on reality. Both positive and negative results advance our understanding. From pairs of black holes that literally shake the universe with their violent mergers, sending ripples through space-time itself, to mirror image white holes that may never exist anywhere except on paper, black holes keep challenging us. They push us to stretch both our instruments and our imaginations, to reach for better observations and deeper theories. From the violent collapse of massive stars to the abstract mysteries of the quantum realm, black holes reveal a universe far stranger, far more extreme, and far more wonderful than we ever imagined possible. We have seen together how they can be as small as an atom, barely existing at all, or as massive as billions of suns, dominating entire galaxies. The range is staggering, almost incomprehensible. From quantum black holes that might weigh micrograms to supermassive black holes weighing tens of billions of solar masses, the span encompasses more than 60 orders of magnitude. No other class of objects in the universe exhibits such an enormous range of sizes. They shape galaxies across cosmic time. They bend the very fabric of time and space around them. And they even test the very fundamental laws of physics that govern reality. Together on this journey, we have climbed through all 5 levels of the hierarchy. Stellar black holes born from dying stars, intermediate mass black holes hiding in the gaps, supermassive black holes anchoring galaxies, primordial black holes potentially born with the universe itself, and quantum black holes existing at the very edge of physical law. Each category tells part of the story. Stellar black holes show us what happens when individual stars die. Intermediate mass black holes, if we can find them, will reveal how black holes grow from stellar remnants to galactic giants. Supermassive black holes demonstrate the profound connection between black holes and galaxy evolution. Primordial black holes might explain dark matter and the rapid growth of early supermassive black holes. Quantum black holes point the way toward a unified theory of physics, each level unlocking a new layer of mystery, each one revealing something profound about how nature works at its extremes. And beyond these primary categories, we have glimpsed the speculative worlds of binary systems and white holes, regions where established science meets imagination, where observation blends with mathematical possibility. The study of black holes is far from complete. Every answer we find raises new questions. Every observation reveals new puzzles. We still do not know what happens at the singularity inside a black hole. We still do not fully understand how supermassive black holes grew so quickly in the early universe. We still have not solved the black hole information paradox, which asks whether information that falls into a black hole is truly lost or somehow preserved. What strikes me most deeply about this cosmic hierarchy is the escalation, the sheer range of scales and phenomena. Black holes are not merely objects of destruction, not simply cosmic vacuum cleaners or gravitational prisons. They are also gateways to understanding creation itself, keys to unlocking the deepest mysteries of space, time, matter, and energy. They force us to confront questions we might otherwise ignore. What is the nature of time near a singularity? How does information behave in extreme gravitational fields? Can the laws of physics as we know them describe conditions at the Planck scale? These are not abstract philosophical questions, but concrete scientific problems that black holes force us to address. They remind us, again and again, that the universe is both profoundly humbling in its vastness and complexity, and endlessly surprising in the phenomena it creates. From the smallest quantum fluctuations to the largest structures spanning billions of light years, black holes appear at every scale, challenging our understanding. Every time we think we understand black holes, they reveal something new. Every time we develop a new observational technique, we discover black holes in places or with properties we did not expect. The universe, it seems, is endlessly creative in finding ways to create these remarkable objects. So now, as we conclude this journey together, I will leave a question with you to contemplate. Which type of black hole fascinated you the most? Which one challenged your understanding or opened your mind to new possibilities? Share your thoughts in the comments below if you feel moved to do so. Perhaps it was the stellar black holes, those cosmic remnants of dead stars, hiding in plain sight throughout our galaxy. Perhaps it was the elusive intermediate mass black holes, still waiting to be definitively found. Perhaps it was the supermassive giants, anchoring galaxies and shaping cosmic evolution. Perhaps it was the speculative, primordial black holes, potentially explaining dark matter. Or perhaps it was the quantum black holes, existing at the very edge of what physics can describe. And if you would like to continue exploring the frontiers of space with me, if this journey has sparked your curiosity about the cosmos, then join me next time. We will venture together into the realm of strange visitors from beyond our solar system, mysterious objects travelling through the interstellar void.